If you need me to read something off, because I see the type is kind of small here. The right one? Sure. Separable differential equation. A differential equation that can be written in the form dy over dx equals f of x over g of y. Solutions. General solution is written using constants. Particular solution solves for the constant using initial conditions. And these give rise to what you call initial value problems. So we're going to do some of those today. We've probably done those before. Anything else hard to read? I don't mind repeating it. So if you can't read it, let me know. So here, you might want to use Desmos. I'm going to ask you to find the general solution to this differential equation analytically. And to get a sense of what it's telling you, I want you to plot particular solutions with constants equal to maybe -4, -3, -2, -1, 0, 1, 2, 3, 4. So first solve this. Then after we solve it, we're going to plot, that's what, 9 different functions on this. Sure. So try and solve that one, and then we're going to plot 9 different functions. So you want to have your iPad out, or phone, something. Pay attention to what you're differentiating, right? Down here, I should not put dx, I should put dt. Yeah.
Could you maybe explain, for those who may have forgotten,
Sure.
kind of the reasoning why it would be dy over dt versus dt or dy? What do you mean behind that?
Sure. Just we're only going to be working with 2 variables, x and y, or sorry, y and some other one, right? So I have y here, and I just have to say to myself, what's my other variable? Well, it's not x, it's t. So differential of y with respect to the differential of t. Yeah. So whatever your 2 variables are here, that's what they need to be here. Okay? That's a good question. I'm going to simplify this actually. Okay, multiplied everything by 2, subtracted over the 2t squared, move the c1 over. I don't care what it is, because it's just a constant. Doesn't matter. So ask a question if you're getting stuck on any of these steps, because I'm skipping some.
So would that be the general solution then?
This is the general solution. Good to point that out. This is the general solution, and you're going to plot 9 of those into Desmos and give me particular solutions. And you get a really cool looking graph when you do that. Has anybody ever taken a picture of the screen on their computer? Ever taken your phone and taken a picture of the screen on your computer? when you plot these, maybe you'll see something here. You might see something you've seen before. Because you notice something that happens with the computer screen. It's all wavy and weird, right? Yeah, so you might notice something when you plot this.
Should we, like,
Desmos can plot two variables. So if you plug this into Desmos, if you plug this into Desmos, probably use X instead of T. Yeah. We'll plot those, and then let's see what it looks like. Oh, no, it's the comma. Cool. So we got some plots going. So make 9 different, you're going to basically make 9 different lines of this, but instead of C, put -4, -3, -2, -1, 0, 1, 2, 3, 4.
Wait, so just plug in right from negative 4.
Yeah, probably -4 to 4. So plot 9 different ones. C negative, C positive, C run. Let's see. So if you plot them, you should get something like this, right? So if you've ever taken a picture of your screen on your phone, I don't know. I've seen this before when I take a picture of my screen. I don't know why we have that connection there. I don't have an explanation for it, but it's interesting. See it pop up again. So again, all of these are representing what? These are all what? Use the vocabulary. All of these different curves are what? They're not differential equations, they are solutions. Yes, they are particular solutions to our original differential equation. Green is a particular one, blue is a particular one, blah, 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 blah. Right? Pretty cool. Yep. Yep.
Y squared over 2 when you integrate it?
Y squared over 2. Yep, I have that right here.
Okay.
Yeah.
Okay.
Yep. So good double checking though. Y squared over 2. And then I just multiplied everything by 2.
Okay.
Yeah. So good to point that out. All right. Ready to move on from that example? All right. Why don't you try this one? Solve the differential equation. That is, find the general solution. Find the general solution of this one. Yes, Avery. Hey, how was your birthday?
Just good.
Good. Anything good to eat?
Yeah. Some pizza.
Pizza.
I gotta take this.
Why did I put this one on there? Let me see. So tell me some things you're thinking right now when you're looking at that. How can we deal with this? Y squared, 1/2 of that minus 1 plus y equals that. How can we deal with that? If I'm trying to solve for y, the only thing I'm thinking right now is complete the square, or maybe I could also do quadratic formula, right? So that's what I'm thinking. I have this, I want to solve for y. How do I solve quadratic? Right? Do the quadratic formula or complete the square. So see if you can make progress on that. Solve this by completing the square and then solve it. Yeah.
Are you solving for y on this one or on the last one?
Oh. Yeah, so for general solution, you have different ways of writing it. You can write y equals something with in terms of x or whatever your original factor was. Maybe it was t, maybe it was x, whatever. You can write it as y equals that plus c, or you can bring it all over to the left-hand side and say y plus x equals c. Doesn't matter. Still gives you the same equation.
So can we not just say 5x?
Yeah, that'd be true, but I want you to solve for y. Yep. So, next. So solve for y. Yes, I'm currently recording it, so they are going to be online. But the notes themselves are not online. I didn't post the notes, actually. So let's see, we had that. Maybe I don't want to factor, maybe I want to complete the square like Jaden said. So let's multiply everything by -2. Let's see, that'd be y squared minus 2y equals -2x cubed. Do I have to worry about manipulating c? No, because it's just a constant. All right, let's see what we want to add. Add 1 to both sides. So that would be y minus 1 squared equals -2x cubed. I added 1 to the right-hand side, right? I added 1 here, I added 1 there. But do I need to account for that 1? No, how come? Because the constant. You got it. So I don't need to worry about that. Plus constant. Isn't that nice? So we have that. Y equals, let's see, square root, then add 1. So 1 plus or minus square root of constant minus 2x cubed. Look right? Do you have any questions on? How we came to the solution?
So you, which, from the red to the red,
From the red to the red.
you took square root, both
Square root.
sides.
Mm-hmm.
Oh, and then added.
Yes. You got it. Any other ones? How did we arrive here? Because I want you to be able to do this. Differential equations are going to be important. Okay. All right. Why don't you plot it too? See what they would look like. Just plot some particular solutions. So play around with Desmos, right? Bring up some pictures of what these particular solutions would look like. You want me to put it on there real quick? So you can...
You do plus or minus.
I don't believe so. Can you? You can only do it implicitly.
That's easier. I don't know how you do plus or minus there, unless you just like graph.
Yeah, just make 2. Do 1 as 1 plus, the other one 1 minus. So let's see. The examples were. Was it 2x cubed? Cricket. So are you plotting some?
I tried to do a plus minus symbol, but it just recognizes it as a zero.
Yeah, so you want to set up two different ones, right? So I'm going to put it on projector. So where you see them connecting, that's one particular solution. This is one particular solution. This is one particular solution. If you want to see how they behave, you can go like this. Y equals 1 plus square root c minus 2x cubed. So if you want to see how they behave in general, just make a constant and then manipulate it. And you can see how solutions behave. Right? These are all different particular solutions given different initial value, given different initial values.
Weird.
Isn't that weird? All right. So before we go on, let me just put this on there for Avery real quick. Okay, so it's right at the front page. Okay, so I think I had some more interesting examples before we leave today. But how are we doing so far? It's all review? Yeah? All right. See if there are any more. Okay, so we're done on that page. Okay, you can do this. Solve the initial value problem. Find the general solution first, then substitute in x equals 0, equal to that, solve for c, find me a particular solution for this initial condition. Find general, then find particular. So if you like seeing the steps right now, that's what we're going to do. Find general solution using C. Use the fact that y of 0 equals 350 to solve for C. Write the particular solution. K is a constant. I didn't write that up there.
Oh.
K is a constant. Sorry.
Unbelievable.
I know. K is a constant. I thought that was self-explanatory. Thanks for pointing it out.
That's
K is not a variable. You could, and you can see what that would look like. But I want you to solve.
And then you'd be wrong. I'm just kidding. I'm not that bad.
Thank you.
Yeah.
I'm just going to stop writing c on the left-hand side because we know we're going to bring it over at the end anyways. So I don't really care about it. Natural log of y equals kx plus constant. Exponentiate both sides. Use what? Exponential properties. We have the general solution. Is it all these steps okay? Over here? Like to right here? Well, I still need to account for it because I'm trying to solve an initial value problem. So I need to keep track of a constant. I could. Are you asking why I don't have it on this side too?
No.
No.
Okay.
You want
I
to
just
keep.
didn't know that you like kept your C. I thought it was kind of just like separate.
No. It's part of it because we exponentiated this side. You have to exponentiate this side. All right. Now solve y of 0. They told me the initial value was 350. 350 equals, well, e to the power of k times 0. That just gives me e to the 0, which is 1. So that means this is equal to e to the power of c. So that means c equals natural log of 350. So you found c. That was the second step. So your particular solution is y equals e to the power of kx, e to the power of natural log of 350. E and natural log cancel out. So 350 e to the power of kx. Particular solution. Do those steps make sense? If not, make sure you ask a question. Yeah, listen.
So your particular solution is just what is your
So given the initial value, if you start at x is equal to 0, this is going to be the curve that is a solution to this initial problem. So all the x and y's on that curve would work for this situation. Does that make sense? Okay. So this is the curve that is going to be a solution to this, given this initial condition of x equals 0, y equals 350.
Your particular solution is just solving for C, or you just put your C values here.
Yes. You want to have no c's left.
So is your general solution D to the K?
Yes, this is the general solution. Yep, very good. How about this? What is the curve? What does this represent anyways? The dy dx. What does that represent? Bring it back to yeah.
The rate of change.
The rate of change. So that means everywhere on this curve, what? The rate of change should be equal to that, right? This is the rate of change for that curve. So just recall what we're talking about when you're doing these differential equations. Does that make sense? Okay. So that's an initial value problem that we just solved. Why don't you work with somebody for 3 or 4 minutes, because this one takes a little bit of algebraic manipulation. And why don't you solve this one? Find the general solution to this, solve the initial value problem. You try that. Might have to use some algebra. If somebody wants to explain it, I know we still got some people who got to get those presentation points, so if you feel like you got this idea down.
Do those presentations have to happen by the end of the semester? Of course. Okay. Yeah. Quarter. Yeah. that.
We're gonna do something a little bit better next quarter too.
We're doing something better next quarter? Can't wait.
Presentations might be a little bit more intense.
Oh, more intense. Can't wait. We should come up with a new mathematical theorem in the class.
But we might have people like grade critique each other. You know.
Oh, I
That'd be good.
can't wait for that.
Like, did I understand?
Could you imagine if we had like, how many kids in this class? 25 new mathematical theorems come out of this one class?
That'd be tough. It'd be a lot. It's ambitious.
We'd be in the news. Be fair.
Yeah, let's don't use that kind of stuff. We haven't learned that yet, right?
That's how I was gonna ask.
It's good. What was this called again? The run? The bosses? I forget those. I definitely can.
So, then, therefore,
We just get to throw the dx in this, right?
Say it again.
Because you know how like test problems usually have dx in there? We just toss it in, right?
Oh yeah, you just have to remember that y prime, that's dy dx. Unless it's a different variable, but you're assuming in these problems that it is with respect to x. Yeah.
Can't mess up.
Oh, maybe if there's something that doesn't exist.
Is it absolute value though? What is the actual law?
So back here.
I'm really not the person to ask.
I thought the formula was 1 over x. We knew about 1 over x is natural log of the absolute value of.
That is true. That is true. But maybe that would come in handy here. Okay, do you want to explain to us then how to get this general solution? This is good. You pulled out cosine.
I don't know.
You got any takers? Possible? Alright, so let's give it a second. And then you say u is equal to sine x plus
that's what I wanted.
Okay, this is all good? That's good. Yeah, these.
I did not want to. I would have been indifferent.
Oh,
Yeah, I could have like a real conversation, but like you have to talk about it.
yeah. So something that, maybe I just pick something that doesn't work. You can get the general solution, but maybe there's no particular solution to this problem. What's it called?
Spiritual sign of that sign.
It's like, oh, it's like a shift in heat.
Yeah.
It's like a kind of
What was it again? It was
like talk about the stuff that I know about.
cosine of x times.
It's like, oh, it's like a stripped down version of heat.
Cosine of x, sine of x plus cosine of that. Oh wait.
Or-
You can get y of 0 equals negative shift.
Right. So we might have a problem here. But it was this cosine of x times sine of x plus 1?
Yeah.
I was able to only get to like 8 minutes. I just I didn't understand. Oh, I would have blocked problem. I'm like, I just didn't understand.
What was the initial condition? 0, what was the y value?
X equals 0, y.
Y equals negative 2? Yeah, so maybe there's a problem there.
Like by the end of like 5 minutes, I was just kind of repeating myself.
Okay, so there is a solution there. And it probably has to do with what Jack mentioned about when you take the natural, or when you integrate 1 over y, right? You actually get natural log of absolute value of whatever you were integrating, right? You remember back to that? So, but let's just stop here for getting the solution. This was y sine of x cosine of x plus y cosine of x. And you do some tricky factoring. What was that? We pulled out cosine of x, sine of x plus 1. Right, you factor out y cosine of x from this. You have this left, divide by the y, multiply by the dx, and you get this line, right? That's just some algebra. Integrate. Most of us in here are going to have to be able to do this on an SL test. So what's the trick I have to use to integrate this if you've forgotten? Use sum. What am I setting u equal to? Good. Sine of x plus 1.
It still doesn't.
Okay, you just do sine.
Huh?
Okay, you just put the sine.
Well, we want this to disappear, right? We want this to disappear, right? So if I set u equal to...
If you give sine of x, then cosine will be du. Cosine of x times dx is d of u.
Okay.
And then
We'll pause there. Sure, there might be multiple ways to do this, but I'm just going to do it this way. U equals sine of x plus 1. I'm not discounting what you're saying. I'm saying you're right. There are multiple ways to do this. But I'm just doing this one because it made the most sense to me. Integrate or differentiate cosine of x dx.
Yeah.
So that means you get, what, natural log. And so this is the important point you might want to remember. Plus c equals, this is u du. So that's what, 1/2 u squared plus c. Natural log absolute value of y equals 1/2 u was sine of x plus 1. Okay, so let's see. If we exponentiate both sides, you get absolute value of y is equal to e to the power of 1/2 sine of x plus 1 squared plus a constant. It would have to be because you took the natural log of this, so the y cannot be negative.
But then once you raise it to the power, does it
This is still a number, and you cannot have y be negative, so yeah, it does get rid of the natural log, but that still has to hold that y cannot be negative. I'm missing a constant on there, but there should be, so I'll just put it here, e to the power of c. So I guess we would have to look at 2 different cases, and then that's probably how we would get the solution. Well, because either y could be positive, or it could be, well, I guess no.
Just plug in -2.
Negative 2? Correct.
-2.
Oh, and then we're just solving.